Okay, same chapter, which is thermal properties. And the topic is Brownian motion. Same chapter, topic is Brownian motion. Definition. The random movement of microscopic atom molecule particles in a fluid, and fluid mean liquid and gases, as a result of continuous collision or bombardment from molecules of the surrounding medium is called Brownian motion. So we can also add here the erratic random movement of microscopic particles in a fluid, mean gas or liquid, as a result of the continuous bombardment from the molecule of the surrounding medium is called Brownian motion. Now, in Brownian motion, for liquids, we will use pollen grains to make this motion visible. And number two, for the air, for the gas, we will use smoke. Sorry, in air, in gases, we will use smoke particles to make the movement of the air visible, right? So I repeat this. Suppose a beaker contains some liquid. This is, suppose, water. And pollen grain is added in the beaker, in the water. So when the water becomes stationary, means stable, we will observe the movement of this pollen grain with the help of the microscope. Under the microscope, this pollen grain is moving like this. Random motion. But for the short period of time, the motion is linear, then it changes direction. Reason behind, the water molecules are colliding with the pollen grain. It moves in one direction. When the other molecule collides with it, it changes the direction. So between two collisions, the motion of the molecule, motion of the pollen grain remains same. So the behavior of this pollen grain, the type of the motion of the pollen grain is actually the motion of the molecule. So this is Brownian motion in the liquid. So the motion of the molecule is made visible with the motion of this pollen grain. Similarly, number 2, if this is the cylinder and it contains the mixture of the air and smoke. So with the help of the convex lens, light is focused on this container with this convex lens, the converging lens. When the mixture of the air and the smoke is seen with the help of the powerful microscope, a bright specks of the light are seen under the powerful microscope. These specks are the particles of the smoke, and they are also moving randomly. Smoke particle is a light particle, lighter than the air, but in the volume is large, so it's made visible by the light. So these bright specks are moving randomly, but again between two collisions, the linear motion. So this is showing the behavior of the air molecules. So for the liquids, pollen grain is used, and for the gases, smoke particle is used, and then it is made visible by the light. So the bright specks seen moving randomly are actually the smoke particles. Okay, the next topic is comparison between comparison among solid, liquid, and gases. So we have to remember these for the questions, okay? The solid has definite volume as intermolecular forces between the constituent particles are very strong. But in liquids, definite volume as intermolecular forces between the particle also strong. Look, intermolecular forces are strong, stronger than gases. But definitely in liquid, it's smaller, little bit smaller than solid, but both are compared with the gases. So the next is no definite volume as the intermolecular forces between the constituent particles are weak. So this is number 1 we have to remember. Next, can diffuse into the liquid. Diffusion is higher than solid, highly diffusible as the particles move randomly at high speed. And the next, number 3, very rigid and cannot flow. Less rigid and can flow. And no rigid and can flow easily. Next, they have definite shape. They don't have the definite shape. They don't have a definite shape for the liquid and gases. Least energy, higher than solid, and the maximum energy. Next, forces are strong, less strong, and the weak. And then strong enough to hold the constituent particle in the fixed position, strong enough to hold the constituent particle in the aggregation within the bulk, but not in the fixed position. This is so fixed position, no fixed position. Extremely low force of attraction, so the constituent particles are free to move in the continuous random motion. And solid, the packed and definitely patterned, so they possess a definite geometry. But packed in the weak comparison to solid, shape not fixed, and packed very poorly, so they fill the container, no definite shape. Okay, now the differences between the solid, liquid, and the gas. Solid as rigid in comparison to the liquid and gases. The liquid is not so rigid. Gases are also not rigid. They have the definite shape and the volume, the same almost. They have the definite volume, but no definite shape, neither definite shape nor the definite volume. Solid particles have the low kinetic energy. Liquid molecules have the intermediate kinetic energy, and they possess very high kinetic energy. Next, they cannot be compressed appreciably, can easily be compressed, can be compressed easily to some extent level, and their molecules are held rigid by the strong nuclear forces. Molecules are held tightly at an intermediate level. Very weak interaction forces are present among the molecules of the gases. Solid are present in a very dense form. Density is present at an intermediate level, but in A level, we consider the density of the solid when converted into the liquid almost the same. I mean, the density of the liquid and density of the solid almost same. And the gases possesses very low density. Solid cannot flow easily, known by the flowing property, flows and evaporate easily. The diffusion rate is very low. The diffusion rate is moderate. Diffusion at the rate of very high rate of the diffusion. So these are very, very important properties and their differences. So we have to remember these ones. Okay, now next topic is specific latent heat. This amount of the heat energy required per unit mass substance to change its state at constant temperature. So amount of the heat energy required per unit mass substance to change its state at constant temperature is called specific latent heat. So specific latent heat is equal to heat energy divided by mass at the fixed temperature. Now, specific latent heat is represented by L, and the heat energy E divided by M. Energy is measured in joule, mass in kilogram, so the unit joules per kilogram. And it can be written as energy is equal to ml, and energy is current into voltage into time is equal to ml, because energy is equal to power multiplied by time, and the power is current into voltage into time, and it is measured in joules per kg. Now, there are two changes in state. Number one is between solid and liquid. Solid to liquid or liquid to solid, and this is called fusion. And the specific latent heat of fusion. And the number two is between the liquid and the gas, or gas to the liquid. So here, specific latent heat of vaporization. The specific latent heat of fusion, sometimes represented as LF, and sometimes this represented by LV. And do remember, the specific latent heat of vaporization for a substance is too large as compared to fusion. Suppose this is the substance in solid form. When it is converted into liquid, there is increase in molecular spacing. How? So the molecules are tightly packed in the solid, but in liquid there is some spacing. So the specific latent heat of fusion is used in spacing increasing. But when this liquid is converted into vapor, into steam, into the gas, there is a complete removal of molecules from the liquid. So it requires a huge amount of the energy. This spacing increase required less energy, but this required huge amount of the energy. That's why the specific latent heat of the vaporization is too large. So the specific latent of vaporization is greater than the specific latent of fusion, because the fusion only changes the spacing, less energy required, but when liquid is converted into the vapor, huge amount of the energy required to remove the molecule completely from the liquid. That's why specific latent heat of vaporization is greater than the specific latent heat of fusion. Now suppose we take ice cube. This is the surface pose table, and this is the ice cube, and it's melting. So it means energy is absorbed from the surrounding. But when it is placed inside the beaker and the external source of the heat is required, so this energy from the heater is current, voltage, and time. Plus, it is also absorbing energy from the atmosphere. So the total energy absorbed by the ice cube is IVT plus absorbed from the surrounding, which is melting it. So this is the actual formula. But in the previous classes, we ignored that absorbed energy is 0. So we wrote IVT is equal to ml, Q is equal to ml, our energy is equal to ml. So this assumption will give you the wrong value. So when you will calculate this specific latent heat by the formula Q by m, mean IVT over m. So this value of the specific latent heat is wrong. It is underestimated. It is smaller than the actual. So all calculations of the specific latent heat based on the O-level syllabus were underestimated. Those values were smaller than the actual. So to correct this, we have to add this absorbs energy as well. Now, again, we will perform experiment twice with a different mass of the ice cube, and we will melt it completely. So first M1L is equal to absorbed A, same heater, same current, same voltage, but will be the time different, T1. And then different mass of the ice cube, same absorbed energy, because No change in temperature of the ice. Ice temperature remains same. Cube temperature remains same. Surrounding temperature remains almost same. So two different times, but the absorbed energy will be same because rate of flow of the heat energy depends on the change of temperature. No change of the temperature, so absorbed energy is same. But for the larger mass, for the different mass, time taken by the heater to melt will be different. Now subtract minus, minus, minus. This is cancelled. So it becomes IVT1, IVT2, M1L minus M2L. So IV is common, T1 minus T2, L common, M1 minus M2. So when we will use this formula, specific latent heat L, IV T1 minus T2 divided by M1 minus M2. So this is the correct value. So the underestimation is corrected. It is fixed now by this formula. Now suppose ice is at minus 10 degrees Celsius. Heat is supplied. After some times, it becomes 0-degree ice. So this is the ice. This is the ice. When further heat supplied, after some time, it becomes 0-degree water. And then when it is converted into water, when further heat is supplied, it will take some time to come to 100 degrees Celsius water. If the further heat is supplied, then it starts evaporation, boiling, so 100 degrees steam. If the steam is collected and heat is supplied, then maybe it becomes 120-degree dry steam. So number one here, temperature is changing. So we will write formula link with MC delta theta. And this C is the specific heat capacity of ice, which is approximately 2100 joule per kg Kelvin. And here, number two, no change of state. So we will use formula related with ml. And here is latent heat of the fusion, which is approximately for the water 336, I think, with 3 zeros, joules per kg. And then in the number three, no change in state, water, temperature is changing. So again, formula mc delta theta, but this is the specific heat capacity of the water, and which is approximately 4.2 joule per gram Kelvin. And then are 4200 joules per kg Kelvin. And then from 100 to 100, no change in temperature, change in the state, water to steam. So again, ml. And this is the specific latent vaporization for the water. It's approximately 226 with zeros, 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 I think so. It will be given on the paper. And then here, number five, steam, no change in temperature. So we will use formula mc delta theta. And this is the specific heat capacity for the steam, approximately same as the ice. So minus 10 to 0, 0 to 0, 0 to 100, 100 to 100, and 100 to 120. So first, change of the temperature, change of the state, change of the temperature, change of the state, change of the temperature. When temperature changes, mc delta theta. When state changes, ml. Now suppose this is time and this is temperature. So initially it is at -10. So this is suppose the -10. So the temperature is changing to 0. And then for this second, 0 ice to 0, no change in temperature. For this period of time, no change in the temperature. And then from 0-degree water to 100-degree water. So this is suppose the temperature 100 degrees Celsius. And then at 100 degrees Celsius water, it starts boiling. And it will take longer than this because evaporation, boiling process requires more energy. So the heater will take the longer as compared to the melting, fusion. And once whole of the liquid is converted into steam, then the temperature of the steam increases and it becomes 120 degree. So here is a change of the temperature for ice. Here is melting of the ice. And here is a change of temperature of the water. And here, boiling, change of the state. And again, change of temperature for the steam. Now, suppose this is the starting point O, this is B, this is C, this is D, and this is E. Between O and A, state is change. So the change in potential energy is 0. Due to change in temperature, kinetic energy increases. So the total energy, internal energy increases. So during this O to A, state is constant. So potential energy change is 0. Yes, they have potential energy, but no increase. Due to increase in temperature, kinetic energy increases. And from A to B, temperature change is 0. So change in kinetic energy is 0, but the potential energy increases. Hence, the total internal energy also increases. Now move to BC. Between B and C, there's a change of the temperature. So there is a change in kinetic energy. So kinetic energy increases. No change in the state. So the change in potential energy is nothing, 0, but the internal energy increases. This is B to C. Again, C to D, temperature is constant. So kinetic energy is constant. Mean the change in kinetic energy is 0. State is changing. So the potential energy is increasing. So internal energy increasing. And now come to the last one, which is DE. Look, change of temperature, So kinetic energy of the steam increases, potential energy remains same, no increase. So the internal energy due to kinetic energy increases. Reason behind internal energy is the sum of kinetic and potential energy we have done in the ideal gas.